the penultimate lesson of Unit 7. We're talking about similarity transformation. Specifically, that means we're talking about dilations, right? So if you remember probably from your Algebra 1 days, there are different types of transformations, right? You can have a translation, which is where you're moving the object. So like we take and translate this shape over. I bet we can go like that. And so you're moving stuff from one place to the other. So this would be a translation, right? We learned those, and then you also probably learned about reflection. That it'd be easier to at the spur of the moment just show you here. So it's where you take it and you reflect it over something, right? But if you want a transformation that creates similar figures, then we're talking about a dilation specifically, right? So a dilation is where the shape grows or shrinks, right? Now, you may or may not have in pre-algebra or in Algebra 1 or whatever else kind of been taught about the center of dilation. So when you dilate a shape in a coordinate system, it dilates with respect to the origin. And so if this was our beginning, if this was our original figure and this was our dilated image, then it looks like it not only gets bigger, but it also moves because it dilates with respect to this. If our origin was centered up here, then it would just dilate straight around it, right? And so that's all that's talking about. You don't necessarily have to know this concept, the center of dilation concept, to solve problems. It just helps us. It just kind of shows us why it seems like the dilation also moves, right? It's because of where the center is, where it's dilated based on, right? And so the scale factor of a dilation is the ratio of the length on the image to a corresponding length on the pre-image. So you may or may not have heard this kind of terminology of image and pre-image. So that's the image is the ending object, and the pre-image or the original figure or whatever is the original before it was dilated, before it either grew or before it shrunk, right? And so that's what we're talking about. So the ratio and it's always the ratio of the image to the pre-image. So if it gets bigger, if the shape got bigger, then the dilation, then the scale factor would be greater than 1. And if it got smaller, then the scale factor, sorry, I keep saying the wrong thing, scale factor of a dilation is going to be less than 1, so something like a half or 2/3 or 3/4 or whatever. So let's do some examples and things. Here we go. So we've got a couple of different dilations here. We want to determine whether the dilation from A to B, so A to B, is an enlargement or a reduction, then find the scale factor of the dilation. So let's take a look at this guy first and do this as our first example. So from A to B, the enlargement or reduction, that's easy, right? Don't have to even think. It's a reduction, right? It's getting smaller, so it's a reduction. So we would expect the scale factor to be between, the scale factor on this one to be between 0 and 1, right? So it's going to be a fraction because it's getting smaller. So let's see if we can figure out what it is. So we do the image to the pre-image. So we need to find a side that hopefully we can just count. If not, then we'll have to use the distance formula and all of that. We won't have to do that on this one. Spoiler alert. We won't actually have to use the distance formula on these two problems, but there will be a problem later where we do. Just wait for that. So this one, our pre-image, has got a length of a half plus 1 plus 2 plus another half, so 3, right? So 3 to the corresponding length on the big one, so it's 1, 2, 3, 4, 5, 6. That would reduce to 1/2. So it's a reduction by 1/2, right? So what about this one over here? Now this one, A is the little one and B is the big one. So this is an enlargement, right? Enlargement. Okay. And let's see if are there any sides that work, right? So this one, we'd have to use the distance formula. This one looks like it's kind of about, right? But it's a little bit wonky. So I think this one's probably not a good choice. This one, we definitely have to use the distance formula. But this one, it goes from point to point. So this one, I think we can just count, right? So let's use this side on the B for the second one, because we use the image on the top. So 1, 2, 3, 4. So 4, 2, 1, 2, 3. So it's an enlargement, scale factor of 4/3. Easy peasy. Let's do something else. So we're going to graph the original figure and the dilated image, then verify that the dilation is a similarity transformation. So this is when we are verifying that dilation is a similarity transformation. What are we checking for? We're going to do this in a minute, but we're checking for whether the sides are proportional, right? They have to be proportional. And so for that, or the angles are equal. And so we can do this with either angle or side angle side or side. Side. I don't know how to count, apparently. It's fine. So I'm going to start by graphing them. That seems like a smart place to start. So let's find A. So -6, -3, -1, 2, 3, 4, 5, 6, -1, 2, 3. So there's A. I'm going to go ahead and label it. It's going to make all our life easier. And then B is at 3, 3. So 1, 2, 3. 1, 2, 3. That's B. And then C is 3, -3. 1, 1, 2, 3. So we have a right triangle. If we were to draw out if we were to find the slopes, we would determine that these are perpendicular, right? So we got a right angle, which is nice. Maybe we're going to keep that information in our head for in a minute. That might save us some time and trouble here pretty soon. We'll find out. We'll find out soonish. So let's do the image. So this is the original and then the image. So we're going to go to -4, -2, -1, 2, 3, 4, -1, 2. So that's right here, right there. And that's X. And then 2, 2. So 1, 2, 1, 2. Great. And then to -2. So we've got another right triangle. So that's hopeful, right? This was Y, and this was Z. Got another right triangle right here. Yep, and then connect there. So these are right triangles. So all we have to know, so we've got all right angles are congruent, right? So all we really need to do is be able to prove that XZ to AC is proportional to YZ to BC. And actually, we want to do it the other way around because we want to do we're not finding the scale factor, but to keep that habit, we'll do that. The proportionality statement will work either way. So we're going to do BC, which is how long? Let's see, 1, 2, 3, 4, 5, 6. So this is 6. And then AC, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And then YZ, 1, 2, 3, 4, 4. And XZ, 1, 2, 3, 4, 5, 6. So we want to know, we know the angle in between them is congruent, right? So we need to figure out is 6, we're going to go, purple to green. 9 to 6, it doesn't matter, but we're going to just keep good habits, right? So does 9 to 6 equal 6 to 9? Not 9, 4, excuse me. So there's a lot of different ways to do this, right? I think in this one, what we're going to do is we're going to cross multiply. So 9 times 4 equals 36. 6 times 6 equals 36. So yes, they are proportional. So yes, this is a similarity transformation. Yay, verified. Great. Let's do one more example, and then we're going to be through. This one's going to be a little bit trickier This is the one I pre-warned you about a minute ago. Right? We got this. We can do it. It's going to be okay. So the instructions are the same. So it's to graph it and then verify that it's a similarity transformation. So we're going to graph it. We're going to find J, which is at -6 and 4. That's J. And then K is at 6, 8. Right there. And then L is at 8, 2. So right there. Right, that's it. Yeah, it's looking good. Okay. And then M is at -4, -2. So there's M. Now you can kind of see why we're ultimately going to end up having to use Pythagorean theorem. Not Pythagorean theorem. Well, it's kind of Pythagorean theorem, but distance formula, because there's nothing that's parallel or perpendicular to any of the axes. So we're going to have to find the distances. It's fine. It's good practice, good things. We got this. You're going to be okay. Just take your time and do it right. Don't make mistakes. Don't miss things that you know how to do. And that's my encouragement there is get the ones right that you know how to do. So 1, 2, 3, up 1, 2, and this is P. And then 1, 2, 3, 1, 2, 3, 4. This is Q. And R is at 4, 1 right here. That's R. And then -2 and -1 is right there. And that is S. Okay. So we're going to draw the connections. Me by holding shift and you by using your ruler, right? Easy peasy. Beautiful. Look at it. It's so lovely and gorgeous. All the things. So there is the original in pink and the, excuse me, and the image in yellow. This is a reduction, right? Very clearly so. I think the other one was a reduction as well. I have to go back and look to confirm that. But let's start finding distances. So we're going to start by finding the distance between J, K. So we're going to use the distance formula, which I will write again up here. The distance formula is D equals the square root of x2 minus x1, so the difference of the x's squared, plus the difference of the y's squared. So y2 minus y1 squared. We made, well, no, I was going to kind of cheat a little bit, mostly because of the amount of space I have. We're doing great on time, but in this video, but I'm worried about space a little bit. We're going to do the distance between distance of JK squared plus squared. So K, the x2 is 6 and x1 is -6. And y2 is 2, and y1 is 4, right? So this equals, I'm going to go horizontally with this to try to, I want to fit as much of this on here, and as long as it's neat enough for you to read as I can, because it'll be easier to see if we have stuff all together. So -6, 6 minus -6, and this really is the reason why I decided to. I was going to do the subtraction bit in my head and talk it out, but it's just not a good idea because we'll miss these ka-chink things, right? So we've got to ka-chink that, so that turns into 6 plus 6, not 0, right? It's not 6 minus 6, 6 minus -6. So that's, yeah. Anyway, I was afraid I was going to make that mistake, and you might make that mistake and whatever else. So we got 36 squared plus 2 minus 4 is negative 2 squared. So this equals 36 squared. That's a big number. So let's pull up our calculator there. Grab it. There it is. So 36 squared equals 1,296. So equals square root of 1,296 plus negative 2 squared is 4. So this equals the square root of 1,300, right? Now, on all the scientific calculators that I recommend for this class, they will be able to do a reduced radical form for you. And so let me show you what I mean. So if I hit second square root of, 1,300 and hit enter. Hold on. Technical difficulties. Be back in like half a I was in the wrong mode. I figured it out. Anyway, most of your calculators will do what I'm about to try to show you, or about to show you. And if not, it's okay. You can still do this problem and make it work and just leave it. Ultimately, I would leave it in radical form if your calculator will give you the exact number. Some of them you have to change a setting and whatever else. You can ask me in the comments or in class if you want to figure out how to do this on your calculator. It's a good idea to be able to do because it's something you'll have to do by hand later, and so being able to at least check your work on the calculator is great. So if I put the square root of 1,300, what I see in this calculator is I get to see 10 times square root of 13. Now, this is actually not very hard to do by hand, and you'll learn how to do that if you haven't done it already, but your calculator will do it for you, which is nice for a problem like this. You can, of course, get the approximate number and get the decimal and all those things. But in this case, the reduced radical is going to be handy because it's going to be easier to compare. And so I'm going to write this as 10 times the square root of 13. Right? So let's do the distance between KL. Distance between KL. We only have to do 3 sides, right? Because if we get, well, I say that is not a triangle, so that's not necessarily true. Yeah, that's not necessarily true at all. If this was a triangle, that would be true. So we got to get the distance on all 4 sides. Is our tear-inducing trauma of these kind of problems. These problems are not necessarily very hard, which is one of the reasons why I was like making a big deal of going slow and getting stuff right that you know how to do. Because these problems are not necessarily hard. They're just kind of tedious, right? So between K and L, so K and L. So X2 is 2, and then X1 is 6 squared, and then Y2 is 8, and Y1 is 8 as well. That one's nice because that does actually cancel this time. So this turns into the square root of negative 2 minus 6 is negative 4. So the square root of negative 4 squared. All right, easy peasy. So, and that's because this one cancels, right? That all cancels out because 8 minus 8 is 0, right? So this will equal. Now this one is even cooler because we've got a square and square root, right? So this actually, the square and square root will actually cancel out of here. It's too late to be recording these videos. Why didn't you tell me I did it wrong? So yeah, I didn't put these numbers in the right place at all, did I? Annoying. It doesn't actually cancel. Let's try again. All right, so 8 minus 6 and then 2 minus 8. I don't know what I was doing, right? 8 minus 6 squared plus 2 minus 8. 8 is the y, right? 2 minus 8 squared. That's going to change. That's going to change what we're doing, and we're not going to have this fun, happy stuff canceled. By the way, just throwing this out there, that last problem, if we had gotten to the square root of -4 squared, then you'd have to do the squared first, because otherwise you wouldn't get a real solution, because as you'd end up with if you just canceled it, you'd end up with -4, and it's not -4, it's actually, anyway. Well, I don't know, that might or may not, leave that kind of nonsense for algebra 2. 8 minus 6 is 2, so we've got 2 squared, which is 4. I'm going to go ahead and hit there. That's easy enough, right? -8 minus 2, or 2, I don't know why I'm trying to do that backwards. 2 minus 8 is 6, -6. -6 squared is 36. Positive 36, because square a negative and it comes out positive. Easy peasy. So the square root of, this turns into the square root of 40. Now, the square root of 40, oops, what have I done? The square root of 40, if you do that little calculator trick, you will discover that this turns into 2 times the square root of 10. This equals 2 times the square root of 10. And I will confirm that for you, just in case you don't believe me, which is probably a good idea, because obviously I'm tired and obviously I'm making mistakes. So 2 times the square root of 10. Great. So the distance between, that's this distance. I should probably go and label these, right? 10 to the square root of 13 times the square root of 13, and then 2 times the square root of 10. Then for ML, distance between M and L equals square root of M and L are these ones. So the x's first, -4 minus 8. -4 minus 8 squared plus the y. So -2 minus 2. Get those in the right place. -2 minus 2 squared equals, I bet we can do the same thing we did this last time and do this. -4 minus 8 is -12, which would be 144 when we square it. -2 minus 2 is 4, squared is 16, so plus 16. These are all kind of coming out real similar, which is similar in a grammatical sense, not really in a math sense. So the square root of 150, which would, if we put in our calculator, we end up with 10. I don't know. My brain is broken. I'm tired. Square root of 150. It's definitely going to reduce. Yeah, 5 times the square root of 60. 6. It's all going to be okay. Great. So that was this one. Okay. Then this guy. Distance between J and M. Is excuse me, is, so J and M, so that's J and M. We'll do the x's first. -4 minus -6. -4 minus -6 squared plus, and we'll do the y's now. So -2 minus 4 squared. So that equals this. I'm not going to just do in my head. Well, maybe once I actually ka-chink, we will. I think we can do it. I think we can pull it off. Let's see what happens. So -4 plus 6 is 2. Squared is 4, right? Easy peasy. And then -2 minus 4 is 6. Squared is 36. So plus 36. It's actually -6, right? But negative times a negative is positive, so it works out. That equals the square root of 40, which we already said and proved that equals 2 times the square root of 10. Now, what I think we're going to do for the yellows is I'm going to go ahead and do it all, and then I'm going to just boop it, And you can either, what I would recommend doing, my recommendation to you is to you go ahead and do the yellow ones, and then like pause it right now. You go ahead and do the distances for the yellow ones, and then unboop it, and then play it, and then we'll boop in the answers, and you can compare. We can see whether you made mistakes or I made mistakes or both, whatever else. I do have a cheat sheet, so I have one up on you. So be back in a second. All right, so booped. So, do your numbers match my numbers, or did one of us make a mistake? I'm pretty sure I did not make a mistake on these. However, you probably already figured this out. I have discovered, after just looking at it and realizing that this is not going to work and checking my notes, I made a mistake on JK and ML. So I'm going to pause again and figure that out and do it over here. I probably will leave this up and do it down here. And then I will boop it when I fix it. I won't know what the mistake is because I erased it. So I don't even know what mistake I made. You can let me know in class or in the comments or whatever else, or not. But I'm going to boop it, fix it. And if you made the same mistake as me, then maybe you can find it. If not, you probably already yelled at me, and we'll move on with our life. So be right back. All right, unbooped. We're still not done with this problem, but there you go. I don't know where I made a mistake. You can let me know or don't let me know or whatever else. But there is the correctness. Now, all that distance formula, the whole point of all that distance formula is to see whether these two figures are proportional. Now, because these are clearly parallelograms at least, now they're almost certainly rectangles. We'd have to find the slopes to prove that for sure. But they're at least parallelograms, right? Because opposite sides are congruent. So we really, technically we've got to check all four sides, but they're going to match. Like if this to this is proportional to this, then it's going to work for these, right? Because they're the same numbers, right? So in this case, let's do original purple to image yellow. So this side to this side. So 4/10 does 4 times the square root of 10 over the one that corresponds on the image. So 2 times the square root of 10. Does that equal this one? So 2 times the square root of 10. 2 square root of 10. Now, the nice thing about leaving this in this reduced form, essentially, is the square root of 10s just cancel on these fractions. 4 divided by 2 also reduces to 2. So 2 does, in fact, equal 2. So they are similar transformations. And it's because all of the sides are proportional to all the corresponding sides are proportional to all of the other sides. They have the same ratios. Great. It works. That's it. It's been a long one, mostly because of this problem, because it's tedious and all of those things. It's been even longer for me because I paused and came back. So I will see you guys in the next one. Have a good day. Bye-bye.